All right, behind me. Good morning. So we're starting on a brand new subject, and actually, compared to pretty much anything else we've done this semester, I think it's like completely new. Like we're not building on what we did before, right? We're going to talk about recursion. Basically, recursion is just when a function calls itself. There's also, you can also have recursion where you have two functions and they each call each other, but we're probably not going to get into that in this class. We're basically going to be doing recursion where a function calls itself. By the way, the other good news I have for you is that this is one of those lessons that I have written notes for, so we're back to that again. Cool. All right, so before I show you an example using recursion, I want to make 4 observations about recursion for you to just kind of keep in mind as we go through this stuff. My first observation is you should only use recursion when you know what you're doing and you're intentionally making a decision that you want to use recursion because it's better than using a loop, right? Basically, recursion. So up until this point, whenever we have had a situation where we had to repeat something, we always used a loop, right? So recursion is just another way of making that same thing happen. But I've seen students who will write a program where a function calls itself, but really the only reason they're doing that is because they can't figure out how to write the loop that would do the same thing better. So as we're going along, you'll get a feel for when it's appropriate to use recursion. All right, so that's my first observation. So I've actually had students who they wanted their whole program to repeat over and over again. So at the bottom of their main function, they just called main, which probably felt to that person like a loop. It probably felt like they were saying, okay, go back up to the top again. But really, that's another function call, and there's a lot of stuff going on there that you don't really want to do unless you're intentionally, doing it on purpose. Okay, second observation. You should realize that recursion actually isn't necessary. You could write any program that we write using recursion can be written with a loop. Okay. The only reason for recursion is just another tool, and in some situations it makes your programs easier to simpler. Let me put it that way, simpler. Easier to read and understand and all of that. Sometimes it makes it significantly simpler. In general, you're going to find that when you write recursion, sometimes it's harder to write because conceptually it's a little harder to get your mind around, but it's going to be shorter probably than when you use iteration. So anyway, any problem you have can be written without recursion, and actually any problem you have could be written without iteration using recursion instead. Just 2 different ways of doing the same thing, and what you need to do is choose which one you think is more appropriate for the particular situation you're in. Usually that's fairly obvious. Okay. Third thing is I'm kind of giving you a sneak preview here. I'm going to be talking about sort of 2 different ways of approaching sort of the analysis of a recursive program. And what we've done so far is pretty much just, okay, we trace through it step by step, right? If we want to debug our program, or if we want to analyze something to see whether it's working or not, we just go step by step through it. You know, we might have a function call, and we might not step through the function every time, because once we know what the function does, we don't have to step through it every time. But in general, we're just plowing through brute force method. So with recursion, you can do it that way, but it's usually not the best way to do it. Usually with recursion, when you're writing your function, and also if you're going back and trying to figure out what's going on with it, you're going to use what I like to call, I think I'm the only person who calls it this, but I like to call it the leap of faith method. Okay? So basically, you're going to when you write recursive functions, you're going to be allowed to assume that the function we are writing already exists. And so we can just call the function that we're writing and assume that it's going to do what we expect it to do. Okay? Now there are some conditions on that. You know, so there are some things that you have to set up correctly in order to make that be the case. But that's basically the bottom line. And that's hard for students to get used to sometimes, right? Being able, like, you know, you're writing a function. Let's see, what's one of the functions that we're going to do? We're going to write a function that reverses prints a number vertically. Okay. Does he do that in the text?
Yeah.
Okay. Yeah. Because I used to use a different text, and so this example was. The example I'm going to do in lecture was different from what was done in the text, and now you'll get the same one twice. But anyway, so when you're writing that, you get to a point where you go, okay, what I need to do next is write a number vertically. Oh, well, I'm writing this function called write vertical, but I can also call it and have it do its job, which is write a number vertically. So we'll be talking a lot more about that, but I guess what I want to say is you're going to want to try really hard to get into the frame of mind where you can use that sort of leap of faith sort of method. Really, it's not a leap of faith. Well, let me talk about that when we get to it, I guess. Okay, so that's 3 observations. My 4th observation is that often when you're writing a recursive function, you may start before you actually have the whole picture of how it's all going to fit together. And there are certain sort of procedures that you use for writing a recursive function. And often you can just, even if you don't understand how it's all going to fit together yet, you can just start going through those steps and filling in the missing pieces. And before you know it, you've got a solution, and you didn't really ever, like, you know, stop and get the big picture on it. So I guess that's a little bit like a leap of faith too. But it's just another way that this is going to be sort of a different approach than what we're used to. Okay, so let's start with a simple example. C++ has a POW function that evaluates expressions involving exponents. So, for example, I just realized So for example, if I say cout 2,5, what's that going to give me? Close.
It would be 32.
32.
Oh, sorry.
Okay. By the way, if you're a computer scientist, there are certain powers of 2 that you just want to be. You want to be able to rattle off powers of 2 pretty quickly, right? So this is one of them. But basically, the way I do that is, sorry, this is a total digression, but it's kind of fun. I know that 2 to the 5th is 32, and I know that 2 to the 10th is 1,024, and basically from there, if I need to know 2 to the 9th, I just go, that's 1,024 divided by 2, right? Right. If I need to know 2 to the 8th, I know I'll divide it by 2 again, it's 256. So I have these like certain ones I know, and then the other ones I can figure out easily. So I don't have to memorize all of them. All right, end of digression. Okay, so we're going to write this function, and we're going to do it. We're going to try to do it recursively. So here's our header, and I'm going to do this just to keep things simple. I'm going to just use integers instead of doubles. We could use a double for the base, and it wouldn't be a big deal. But let's just use ints, and I'm going to assume that the exponent is always greater than or equal to 0. Okay. So our two parameters there are base and the exponent, right? Okay. So here's the first step in writing a recursive function. You figure out what the base case is. So what's a base case? A base case is a situation in which you can immediately, without any difficult computation, just return the correct answer. And a good base case is the absolute simplest one of those. Does that make sense? So for example, for my base case, I could use when exponent is equal to 3, because I could just say return base times base times base, right? Does that make sense? But that wouldn't be a really good base case because I can go simpler than that, right? So what's the simplest situation here that I could possibly think of?
2 to the 0, so it equals 1.
That's correct, 2 to the 0, except don't say 2, just anything to the 0, right?
Yeah.
So, in other words, when exponent equals 0, right? That's my base case. So, the general form of a recursive function is always going to be if base case, do the base case, else, and then here's the recursive case. Okay, basically every recursive function is going to have that general format. There's going to be variations on it. For example, maybe sometimes there'll be 2 base cases instead of 1 that you have to handle. Maybe sometimes there'll be 2 recursive cases instead of 1 that you have to handle. Maybe sometimes the base case is that you do nothing. So instead of doing it this way, you would just have a reverse of it so that it would only show the recursive case, because in the base case you don't want to do anything. Anyway, there's different ways this will show up, but basically this is the fundamental structure that every recursive function is going to have. It's always going to have a base case and a recursive case. So our base case was if exponent is equal to 0, and if exponent is equal to 0, what do we want to do? Return 1. Okay? Let me look at my notes and see if I forgot to say anything. All right, I guess just one other thing about the base case. I think this is obvious, but just to make it clear, the base case has to be a situation where you don't have to make a recursive call. Yeah. Okay. Let's talk about the recursive case for a minute here, okay? I know that an important rule about writing recursive functions, and this is that condition that I was talking about before, right? Remember when I said you could call a function, I could call the PAL function and just assume that it works, okay? The only condition on that is if when I call it, it's getting me closer to the base case. Okay, so I can't just say return pal base exponent. Done, right? Because it's not getting me, I'm calling the same pal, it's not getting me any closer to the base case. The whole reason that recursive functions work is that each time I do the recursive call, I'm getting closer to the base case, so eventually I'm going to stop. Okay? So if I had to pick one observation that was the most important one for you to get, that would probably be it, right? When you write your recursive case, you got to be getting closer to the base case somehow.
Just want to get straight. So when you're doing a recursive function, you have to make sure that eventually it'll end up at the base case and eventually it'll stop.
Correct.
So it has to eventually return 1 at the end of it.
Correct.
Okay.
Yeah. Okay, so there's a couple other, so that's one hint, right? So trying to figure out what statement goes here. By the way, notice that we haven't really even thought sort of in general terms about how this function is going to work. Well, we're already almost done with our function, right? Just kind of sort of by going through the step of figuring out what the base case is going to be. Now, I know that this is a value returning function, so it's probably going to have a return statement here, right? I'm going to be returning something. Okay. What else can you tell me about what's going to go here? I don't want to know the answer, just like make an observation about what's going to have to be involved here. Yeah?
I think you're going to times base by itself and then also have exponent minus 1.
Okay.
You're going to all to power.
Okay, so that's all either correct or close. So let me, to do it sort of more incrementally, I guess I would say, another observation is I'm going to have a call to the function pal in here somewhere, right? It's a recursive function, that's probably what's going to happen. So I'm going to go ahead and put pal here. Okay, so really all I have left is trying to figure out what the rest of that expression there is going to be. Okay. What can you tell me about, what can you tell me about not mentioning the word base or exponent or minus or plus or anything like that? Make an observation about what's going to go in those parentheses. What is it, whatever we put in those parentheses, what is it going to have to do?
Change.
Okay, change. So it's not going to be just base and exponent, right? And change in what way?
So it gets closer to the base case.
So it gets closer to the base case, right? And since the base case is when exponent equals 0, probably we're going to be, what we get put in there is going to be some sort of a variation on exponent that makes it smaller, right? Any guesses what that might be?
The exponent minus 5.
Close. It's going to be the exponent minus 1. Okay. And it's not always going to be minus 1. You know, sometimes it might be, divided by 2 or something like that. But in this case, if we're thinking ahead a little bit, we can think, okay, we have to multiply base times itself, exponent times. So we're probably not going to want to get closer. We're going to want to get closer to the base by, closer to exponent being equal to 0 just by 1 each time. So it kind of makes sense. And I'm going to say something like this. Okay, I'm going to get rid of that because I'm not trying to say that I'm done yet. Okay. Okay. So let's look at that and think about where that puts us. Is that correct? Okay, that's not quite right. It's not true that base to the exponent is equal to base to the exponent minus 1, right? But it is true that base to the exponent is equal to base to the exponent minus 1, and then what do I have to do with that? I have to adjust it somehow, right? Times base, right? Let me put it in front, I guess. Okay. Does that make sense? I mean, just looking at that one, forgetting about everything else and just looking at that one statement, what I'm saying there is that base to the exponent is base times base to the exponent minus 1. Or I guess if we were to put that in algebra, we might say something like x to the n equals x times x to the n minus 1. That make sense?
Yep.
That's the algebraic equation that we're applying here. Okay, any questions so far? Okay, so I think we're done. Right? Let me see if I forgot to say anything here. Okay, let's put this in a real program so we can test it out. Does that look okay? Okay. $32. Okay. Any questions or observations about any of that? Look easy, look hard? Get a few more. What I want to do next, actually, is I want to show you a couple ways of looking at recursive functions more closely, sort of analyzing them in detail, stepping through them. Okay? This is that other method. So basically what we just did is we just used the leap of faith method, right? We assumed that we had a function named pow that did what we expected it to do. What I'm going to do now is I'm going to actually show you a couple of tools that you can use to actually trace through what's going on here. There's a couple reasons for this. One is that this will give you a, sometimes seeing this will give you sort of more of an intuitive feel for how the recursion is actually working. Take a little bit of the mystery out of it. Okay. The other reason is that hopefully this will be very rare, but sometimes you may have a situation where you just can't figure it out and you need to be able to just step through it step by step and see what's going on. Okay. A third reason, I suppose, is that there might be a question on the final where I give you a recursive function and say, what does this do? Okay, so I'm going to come over here to Paint, and I'm going to make myself a table. No, I need to be bigger than that. And it's going to have 3 columns. Okay, the first column here is going to be the function column. The second column here is going to be the intermediate result. Look at that, I made it just the right size. And then the third column is going to be the final result. Okay? So part of what happens when you call a recursive function is you're doing some sort of a calculation, and then you sort of have to put it aside for a second because you're doing the function call again. And then in the process of doing that function call, you're doing some calculations, and then you have to put that calculation aside for a minute because you're going to call it again. And it kind of goes down like that. So that's why we have here 3 columns. We have sort of that intermediate result, and then we have the final result when we get done with the recursive function call and come back. So let's analyze what happens when we say PAL 2, 3. Okay? So we look over here in our function. If base is 2 and exponent is 3, we don't do the base case, we do the recursive case, right? So what we're going to return is 2 times PAL of 2, 2, right? So I'm going to write that down as my intermediate result. 2 times PAL of 2, 2. Okay? Now, we can't do our final result yet because we don't know what PAL of 2, 2 is. So we're going to go over here and say, okay, well, I need to figure out what PAL of 2, 2 is. So let me put that down. PAL 2, 2. Okay? So now we go back and look at our code because we're trying to figure out what PAL of 2, 2 is. And PAL of 2, 2 turns out to be 2 times PAL of 2, 1. 2 times PAL of 2, 1. Okay? Now, we can't do the final result yet because we don't know what PAL of 2, 1 is, right? So we've got to figure out what PAL of 2, 1 is, so we put it over here in our function call, PAL of 2, 1. Okay, so we go over here to look at our code to see what PAL of 2, 1 is. It turns out that PAL of 2, 1 is 2 times PAL of 2, 0. So we put that down, intermediate result, PAL 2, 0. Okay, but we don't know what PAL of 2, 0 is. So we've got to figure out what PAL of 2, 0 is. So PAL of 2, 0. What's PAL of 2, 0? If I look over here at my code, now I see exponent is equal to 0, so I'm returning 1. So now the answer is just 1, and I know that my final result is 1. Right? So but now I can start going back up the table, right? Now I can say, well, 2 times PAL of 2, 0, PAL of 2, 0, I just figured out that's 1. So 2 times 1, that's 2. Okay? Now I want to figure out 2 times PAL of 2, 1, but it says right here that PAL of 2, 1 is 2. So this is 2 times 2, which is 4. And so now I'm back up here, and my final result is going to be 2 times PAL of 2, 2. PAL of 2, 2 is 4, so this is 2 times 4, which is 8. So now I know my final result for PAL of 2, 3. Okay. Another way of saying this is that when I'm trying to find out what the result of a recursive function is, there are a bunch of other results that I need to figure out first, right? I need to figure out what the result of that recursive function call is in a smaller case, and then in a smaller case, and then in a smaller case, before I can figure out what the final result is. Okay? So I have found that this table works. You have to sort of be creative with it sometimes, but I've been able to make it work for just about any situation. Sometimes a recursive, I mean, this case works well in the table because it's a value returning function. Sometimes it's going to be like a function that prints something out, in which case you might have to figure out some clever way of representing what's been printed out on the screen or something. But usually I can make this work, and it works pretty well. Any questions about that table? One other observation that I forgot to make about recursion, and that is that when you start trying to trace through the recursion in a very detailed way, there's not much I can think of that's more tedious than that. So make sure you get lots of sleep before a lecture next time. And there's no way around it really sometimes. You just got to kind of plow through it. So I apologize in advance if my voice starts sounding like I'm saying the same thing over and over again at some point here. All right. So I want to show you another way of analyzing the power function. And this one is actually going to be, what we're going to do is we're going to actually draw pictures of what's going on inside the computer. Which really means there's a lot of, in this case, with recursive functions, there's usually a lot of stuff going on the stack. Right? And when we talked about pointers, we talked about the stack being where all of the automatic variables, all the local variables go, and the heap being where all of the dynamic variables go. So now we're going to be focused on the stack, and we're going to be talking about how the stack grows and shrinks as I call functions. Okay? The basic way that the stack works is each time I call a function, I put a new block of memory on the stack that stores all of the stuff associated with that function call. Okay? If I call the same function again, that doesn't mean I just leave that block there. I have to put another block on top. So if I call pow 6 times, that means I'm going to have 6 blocks of memory on the stack, each of them representing a different function call, a different call to the function pow. Those blocks of memory are called activation records. There's another name for it too, and it's escaping me at the moment. But we can call it an activation record. Frame, stack frame? I can't remember for sure. Anyway, activation record works. All right, so let's, I'm going to get rid of this table. And so here's the bottom of my stack. I'm going to change my main function just a little bit to make it a little more interesting. I'm going to say int result get pow 2 comma how high should I go here? I'll just go to 3. 2 comma 3. You can imagine in the table I just did, I only went to 3. Right? So you can imagine if I'd gone to 5, we would have been here for a while longer, and I would have been saying the same thing over and over again. So I'll just stick with 3 here. And then I'm going to say cout result. Okay? So over here on my stack, actually I might as well just play it safe and make this big. The first thing that goes on here is going to be an activation record for main. Okay, there's my activation record for main. What goes in here is going to be my local variables. So, whoops. That's one local variable named result. And then the other thing that I'm going to put in here is I'm going to make because I'm calling a value returning function, I'm going to put a space in here for the return value of that value returning function. Okay? In an actual compiler, it might do something different, like it might put the return value in a register someplace or something like that. Or it might do it. It could do it like this, depending on how you write the compiler. But actually, it's been a while since I did compilers. I think if I remember correctly, it's going to do it. So I'm putting these two variables in an activation record and just kind of drawing them abstractly. Really, the way the stack is working is that each thing you put on the stack, like I would be putting result on the stack, and then I'd be putting the next thing on the stack, and then the next thing on the stack. So the activation record would actually be again, the way I should probably be drawing it is just a bunch of vertical lines on the stack. But I'll let myself be a little bit abstract here. So here I'm just going to put RET. I'll put RET to represent. That's where I'm going to put the return value of that function call. Okay. So my next activation record is going to have some way of going back and putting the result in this box here. Okay. All right. So what's in result right now? I'm not going to write it in there, but it really should be a question mark, right? Junk. Same thing with the return value. So I've done this declaration. Now I'm going to do this statement right here, which involves a function call to the POW function. So whenever I have a function call, that means I put another activation record on the stack. Okay, so here's my activation record for that first call to the POW function. What's going to go in here is my two local variables here. Yeah. I got to figure out a way to put 4 of them in here. 1, 2. So my two local variables are base and exponent. Okay. Then what else is going to have to go in here? Yeah, I'm going to have a place for when I call this function, I need to set aside a place for it to put its result. Okay, that's what I'm calling return here. Oop. Okay, and then the last thing I need, and this is the only other thing that I need to remember, is I need to remember where this was called from, so that when I finish this function up, I know where to go back to in the execution of my program. Okay, so the way I'm going to do that is I'm sort of abstracting what's really going on the stack, but I'm going to call this here place 1, because that's one place I call POW. And I'm going to call this here, I'm going to call this place 2. And so I'm going to say called from. Okay? And in this particular case, I was called from place 1, right? Okay? So I was called from place 1. Base is equal to 2. Exponent is equal to 3 the first time I get called, right? And I'm waiting for my return value. Okay? Let me just say that I warned you it was going to be tedious, right? But you know, if you can follow this, this is actually pretty important stuff, right? I mean, you're going to study this again when you study assembly language. You're going to study it again when you study compilers. This stuff about how the stack works is pretty good stuff. So, okay. So now I'm inside my PAL function, and I'm going to start executing the statements inside my PAL function. Exponent doesn't equal 0, so I'm going to do the else part, and the else part involves a call to the PAL function. So let me make an activation record for the PAL function. Okay, and then I'm going to have those same 4 things. They're going to be called the same that they were before. Base, exponent, return, called from. Okay, what's base? 2. What's exponent? Exponent's 2 now, right? I'm waiting for my return, and this is called from place 2, right? Okay, so I've got my activation record set up. Now I'm ready to start executing my function. Exponent's not equal to 0, so I do the else part, which means I have to call PAL. So, but this time I'm calling it with base is 2 and exponent is exponent minus 1, which is 1. Base is 2, exponent is 1. Oops. Gonna run out of room. Okay, so base, exponent, return value, called from. Okay, base is 2, exponent was 2, but I sent exponent minus 1, so now it's 1. Return, I'm waiting for my return, and this is called from place 2. Okay? So, now I have finished setting up my activation record. Now I'm going to start executing the statements inside PAL. Exponent's not equal to 0, so I come down here to the else part, which means I'm going to have to call this function named PAL that we haven't seen before. Okay, so I'm calling this function named PAL, which means I need to set up an activation record for it. Going to have 4 things in it, and my activation records keep getting smaller and smaller. Okay, same 4 things. Base, exponent, return, call from. Base is still 2. Exponent is 0. Waiting for the return value. Actually, in this case, I'm not going to need a return value, huh? Called from place 2. Okay, so now I'm ready to start executing the statements inside PAL. Now, exponent is 0, so I know that I'm going to be returning 1. And that 1 gets put back here in the previous activation record, so put a 1 there. And now I'm done with my function, right? I returned 1. Now I'm done with my function. So what happens to this activation record? It gets popped up. Yeah, this actually does an excellent. I just remembered that we just studied stacks. Yes, it gets popped off the stack. So it looks like this. Okay? So now I'm ready to go back and finish executing my PAL function. I look here to see where it was called from. It was called from right here. Okay? So what I'm returning is, what I'm going to do next is return base, which is 2, times the return value of that function call, which is 1. So what I'm returning is 2. So that 2 goes back down here. And now I'm at the end of my function, so I pop it off, that activation record off the stack. Oops, got a little carried away there. Okay? So now I'm ready to go back and continue execution of this function call. I see that I was called from place 2. So that's down here. So what I'm doing is I'm returning base times the return value. So I'm returning 2 times 2, which is 4. So the 4 is going to go down here. Now I'm done with this function call. So I pop the activation record off the stack. I'm sure that there's probably a very easy way to just make the eraser bigger. It's probably under that size menu over there. Okay, so now I'm ready to continue execution from where I left off here. Here I was called from place 1. So I'm doing something not quite right here, because we should be down here, right? We still have to say return base times the function call, the return value, right? So let me think about that for a sec. But so what I'm returning is 2 times the result, which was 4. So what I'm returning is 8. So the 8 goes down here. Whoops, not 9, 8. And now I'm done with this function call. So I pop that off the stack. And I guess so what I was doing wrong is that called from place, what that should have told me is where I continue on from after I return the value. So I was sort of getting it off by 1 there. So now I was called from place 1. So now I'm up here at place 1, and I'm in the middle of executing my statement. Result gets this function call, right? The return value of the function call is 8. So what I'm saying is result gets 8. Okay? And now I say see out result, and 8 comes out on those. Great. Probably should have done it with 2 to the 4th instead, huh? Any questions about any of that? I know that probably, my guess is that most of you probably do not follow every detail of that, and that's okay. I would suggest taking a look at the, going in and taking a look at the recording and going through it until you really get it, because it's just kind of pretty fundamental stuff we're talking about here. Any questions? Yeah.
How simple is it to get stack overflows using recursion and things like that?
How simple is it?
Or how easy is it? Does it happen often?
Does it happen often? It doesn't happen often.
Okay.
You'd have to have it probably, if it happens, it's because you have an infinite recursion. That's usually when it happens. I'm trying to think if I've experienced that, and I can't remember other than if it was an infinite recursion, and I don't think I have. So. Okay, let's take a break. Let's see, that clock says 9:33, so I'll start when that clock says 9:45. Yeah, that clock is really fast too, huh? Anyway, I'll start when that clock says 9:45.